Okay, I think we're ready to go now. So we kind of started out with just the data process. Chapter 1 was more of an overview of statistics. Chapter 2, we started going through the data process. We designed an experiment. We collected data. We didn't actually physically collect data. But we talked about how you would do that, etc. Now we're going to start looking at graphical methods for describing the data. This is kind of like that first step, that branch that we said was descriptive statistics. We're just trying to see, how does the raw data look? Are there any patterns we can pick up on? What's just essentially a quick and dirty graph we can do to help visually summarize it. So first, we're going to look at categorical data. Just because there's only a few types of graphs that will work with categorical, and then on the numerical side, there's a whole ton, like a whole other science behind doing numerical graphs. So first, let's get categorical out of the way. I will say, if you're a perfectionist and you like drawing straight lines, you may want to get something out that has a straight edge on it. If you're not a perfectionist, then don't worry about it. So data types. We have categorical and numeric. That shouldn't be anything new. What did I say? When I said this, I was mainly talking to dual credit. But what did I say was another name for categorical variables? What's that? Qualitative. Yep. So categorical are also known as qualitative variables. Numeric, quantitative. Now for categorical, which is any non-numeric data, you can use frequency distributions, bar charts, and pie charts. We'll spend quite a bit of today looking at these two, bar charts and pie charts. And then for numeric, it's anything that can be measured and listed by number. We've already looked at dot plots some. We'll get into stem and leaf plots, frequency distributions, and then histograms. Notice that you can do frequency distributions for both of these. Let's look at categorical. So we talked about this in chapter 1 when we did the bar graphs. If you remember, like that ice cream example that we did, what's your favorite flavor of ice cream? That walked us through how to create a bar graph. But just as a review, remember, you got to title your graph, label your axes. So your horizontal axis, the x-axis is your categories. Vertical axis can be counts, meaning the frequency. Proportions, the relative frequency, or percents. And then scale your axes. I don't remember who else I'll do it. I know it was someone. The only homework I grade by hand is AP, so sorry to throw y'all under the bus. But someone in AP Stats gave me a graph that had their tick marks evenly spaced, but then they said like 27, 28, 32, 36, 37. Like, so you're telling me that gap between 27 and 28 is the same as the gap between 28 and 32? That's a little misleading there. And make sure you scale your axis appropriately. And then you draw vertical bars to represent counts, proportions, or percents. So let's first look at comparative bar charts. Again, especially this comparative one, you've probably seen them before. You didn't think too much about them. You're just like, oh yeah, okay, I know how to read it. No big deal. They're pretty self-explanatory in the reading of them, but some things to look at. So when do you use them? You use them with categorical data. How do you construct them? It's just like a bar chart, but you're going to have two or more groups that you're comparing to each other for each category. Like on the ice cream example, that would be like saying we wanted to look at the favorite ice creams in boys versus girls. So you'd have a bar for boys, you'd have a bar for girls for each flavor. You must use the relative frequencies on the y-axis. Why? Can anyone think of why we have to use relative frequencies? What happens if I interview 12,000 boys with only 3,000 girls? And I try to do that ice cream graph. But I just use counts.
You're going to get a lot lower counts for girls.
Yeah, the girls are going to look like they're down, not really amounting to much, and then the boys are going to be way up. They're going to be all your tall bars. Relative frequency levels the playing field. Everyone stands a chance then. So we use them to make relevant comparisons regardless of what sample size you have. And I need a key to denote the different types of bars. So if you're one that you like pretty colors, maybe you want to get some pretty colors out. If you're one you're, I'll just color one and leave the other blank. That works too. Let's look at this first example. So each year, the Princeton Review conducts a survey of students applying to college and of their parents of college applicants. In 2009, they surveyed 12,715 high school students and asked them, ideally, how far from home would you like the college you attend to be? Also, 3,007 parents of the students applying responded to the question, how far from home would you like the college your child attends to be? And they displayed this data below in this frequency table. So just before we even do the graphs, what do you notice here between parents and students? Yes.
Like more students rather stay closer to home than further away from home.
Yeah.
Same with parents, they want their child closer to home than away from home.
Mm-hmm. Yep. Yes.
There are more students than parents.
There's more students than parents. That's right. So we've got to equal the playing field. So to do that, what do we have to find first? Relative frequencies. That's right. So if you have your TI-84 that you checked out from the library, you can use that, or you can use your phone, your calculator on your phone. Because this is just simple. From this point forward, since we're doing calculations, I highly recommend bringing your 84 with you. I know we haven't done much with them, but now we're going to start getting into math. So, you may want to...
When this first table started already?
Yes.
Okay, thank you, everybody.
We just started that example. Okay. Let me go back. I have this one. I just need to erase stuff. Y'all aren't seeing any of this at all.
All right.
Okay, they gave us the total, so really we don't have to add everything up because they tell us how many students and how many parents there are. So how do we calculate relative frequencies? Anyone remember? The what?
Part over whole.
Part over whole, that's right. So for this first one, I would do 4450 divided by 12,715. What would that be rounded to 2 decimal places? 0.35, good. I'm going to just write it on the table, kind of to the side here. 0.3. What about the next one? 3942. What's that relative frequency?
.31.
0.31. The next one?
.19.
0.19. And then the last one for the students.
.15.
0.15, that's right. Okay, so we did our relative frequencies for the students. To save us a little bit of time, I'll go in and write the ones for the parents up there. That way we can have them. But you would do the same process for the parents. And you should get 0.53, 0.30, 0.11, and 0.06.
You said 0.06?
Mm-hmm. So now we've leveled the playing field. Now that we have relative frequencies. Excuse me. We want to take those and make a comparative bar chart with it. So I'm going to go make my axes.
Aside from the example, we haven't written anything else down, right?
The only key thing we wrote down up here was when to use categorical data.
Okay. I can do that.
If you wanna, if I grab a picture of that. You know, mine's the only two things. Okay, so there's our axes. What goes on the vertical axis? What would my title for that axis be? Relative frequency. What about the horizontal axis? Distance. What units is our distance in? Miles. I'm going to put that in parentheses, that way we don't have to write miles every time. Okay, so we put our different categories in here. We have, here we're going to have the less than 250 miles. Then we'll have 250 to 500. $500 to 1,000. And then at the end over here, greater than 1,000. Now, if we look at our relative frequencies, what's the highest one you see? 0.53. So all we have to go up to here, really, I'm going to say is 0.6. So halfway would be 0.3. 0.1, 0.2. 0.1. We're going to count by tens here. Tenths, I should say. Okay, now here's where the different colors come in. We've got to do one for boys and not boys. One for students and one for parents. So for me doing the graph on here, I'm going to do just a solid blue square for students. And then for their parents, I'm just not going to color it in. So I'm going to do just a blank. So that's our key or legend, whatever you want to call it. Now we start drawing the bars. So for the less than 250 miles, what was the relative frequency for the students? 0.35. So I'm going to come up here to about 0.35. It's a little bit higher than I wanted. I need to move it. Okay. What did the parents say for that same distance, though? What proportion of the parents said that? About 3. I need to move that. Okay, there we go. So there's parents and students. Okay, now we go to the next distance, and I think I made my boards a little too wide. So for the next distance, what proportion of students said 250 to 500? 0.31, so just a smidge above. I'm gonna have to, y'all bear with me. Keep graphing it. I'm gonna have to redraw my graph because this size is bothering the heck out of me. Point 0.35. Parents is 0.53. That's not good enough. Then we said 0.31. Mr. Schultz, okay, let's see here. What was it for 250 to 500 for students?
1.5.
No, it's
0.31.
I'll do it. Yeah.
Okay, and then what was that same one for parents? Next category for students? 0.19. For parents? And then the last one for students. And parents is like 0.06.
Yeah.
This is a lot easier when you're up close. Okay, there. That's roughly how it should look.
we done a comparative bar chart class or just bar charts?
We've just done bar charts in here. If it looks familiar, if you're thinking this kind of looks familiar, you've probably done it in other classes. This shouldn't be completely new. You just didn't really formalize it with all these fancy terms. It may be completely new. Okay, then what are we forgetting of? Our chart looks good and all, but what's the one thing we're forgetting? Title. What do we want to call this? What did they measure? Distance. So sure, sounds good. Let's say college distance from home.
Maybe preferred college distance from
That works too. Okay, now let's make some observations about this chart. And this is actually the next question on on page 2. But while the chart's up here, what are some things that we've noticed now that we have the chart drawn?
parents like their kids closer.
Yeah, parents want their kids closer to home. Where do kids tend to want to be, though? Some want to be close to home, and some want to get out of Dodge and burn tires on the way out. So let me go back to the PowerPoint. Okay, so I kind of did this with y'all. They walked through it here, but I feel like it's probably more useful if we actually walk through it together rather than here. This is how you do it. We did that. Let's go back. Okay, so what does the graph show? We already talked about it. Parents tend to want their child closer to home. Students, though, tend to want to be a little bit further from home than the parents would like. So like I said, that's that question on the top of page 2. I'll give you a second to write that in there. But I guess I did. No. Fine. Okay, next let's look at segmented, or they're also called stacked bar charts. We also use these with categorical data. And they're made similar to bar charts, but of course, first, just like we did on the other, we must calculate the frequencies. And then for each group, we'll draw a bar that represents 100% of that group. And then divide the bar into segments that correspond to the relative frequencies of the categories. So, let's look back at our college data. And we're going to draw a stacked bar chart now. So we'll do this one. Or I guess let me ask, what would y'all rather do? Would y'all rather us do it together and I'll walk y'all through it, or just click through the PowerPoint and what would y'all rather? Go over it? Okay. I feel like the PowerPoint's just a little too rushed. Okay, so I'm not gonna redraw the chart because y'all have it on y'all's notes. But we still start our axes almost the same way. Wrong way. Okay, so the difference here is instead of having 4 different groups, we're just going to have 2 down here. Students and parents.
Oh, I know.
And then we're going to have to go all the way up to 1. So I'm going to try to draw these as evenly spaced as possible. This will be, again, our relative frequencies. Now we need to draw a bar that goes all the way up to 100%, or 1, I should say, for both of them. Okay, so there's our 2 bars. We've kind of got them lined out now. So for the first category, the less than 250 miles, what proportion of students said that's where they wanted to be? What was our relative frequency for that first category? 0.35. So on that bar, we'll go up to 0.35. Draw a line across. Bless you. And then we'll need to color that one in some color. I'm going to do light blue. I said light blue. It doesn't have to be perfect as long as you know what it's. Okay, close enough. For that same category, what proportion of parents said that? 0.53. So we'll go up to parents, and at 0.53, that's where we'll put the line. And yes, we'll color that part the same color because it's the same category. And we'll need to also include this in a key here that says this color means less than 250 miles from home. And good enough. So I'm going to come over here, say, okay, that color my main writing is in purple, less than 250 miles. Then for the next one, our next category is 250 to 500 miles. I'm going to do that one in green. Oh no, let's do orange. My screen might burn a hole with me using this color orange in it, but that's okay. Now, I need to figure out where to draw those lines. So what I want y'all to do is, since we're on the second category, we'll add the first and second together. So like for students, we would do 0.35 plus 0.31. What would that get you? 0.66. So on 0.66, that's where I'm going to draw my line across. And then I'm going to color in this section. With this orange. And then I'll take the same approach for the parents. I'll add 0.53 and 0.30. Going to give you 0.83. I'll go up there, and that's about where my line will be up there. And I'll color that in. Then we go to the third category. And I'll need to add 0.35, 0.31, and 0.19 together. Now tell me where the next break is. I think that's 0.85. And I'll do that one in green. Which means for parents, I'll need to do a line at 0.94. Green represents 500 to 1,000. And then, just to save time, because by now y'all may be tired of using different colors, we can just leave the other one white. That's a color. White's a color. So we'll just leave it plain. Save some time. So if it's just white, that's going to be greater than 1,000 miles. And then don't forget, we still need to put our title here. So maybe we say ideal distance from home or whatever. Ideal distance for college, whatever you want to call it. And if we look at this stacked bar chart or segmented bar chart, if you notice, it says the same things that we said on the comparative chart, the first one we drew. More of your parents want their child closer to home than what the students want.
Yeah, because they got smaller rooms.
Exactly. I mean, this. If you look at the parents, like a bunch of your parents want the child closer to home. Students, not a little over halfway. Then it really shoots up again. Students, not quite as much. Then just a very few are okay with them being more than 1,000 miles away. And this is just my own 2 cents for what it's worth, but I know when I was in y'all's shoes picking colleges, I was super close to choosing Baylor. And my parents were like, okay, you can go to Baylor, but you got to get a job to pay for what the difference would be over going to A&M. I'm like, wait, so you're telling me I'm not, like, we'll pay for everything if you go to A&M. If you go to Baylor, you got to get a job to pay for the rest. But, okay, looks like I'm going to A&M. And then every time I would go home and then come back, I would get to A&M. I'm like, just think, if I had to go all the way to Baylor, I'd only be halfway home by now. But I'm here. I don't have to drive that far. Anyways, let's go back to the PowerPoint. No, not that. So they were walking us through it, but we already did it. And again, notice that this displays the same relationship as the double bar chart does. So bar graphs show a bar that represents either count, proportion, or percentage of each category. They may or may not show all categories. However, if we use a pie graph, it shows how a whole divides into categories using either proportions or percentages. So on a pie graph, you must include all categories. In case you didn't catch that, that's a blank at the bottom of page 2. All categories. So that's what we're going to look at now at the top of page 3, pie charts. So leave your colors out. You may still need them. So when do we use a pie chart? Again, when we have categorical data. How do you construct one? Well, first you got to draw a circle. That's the shape of pie chart's in, a circle. And we have to calculate the size of each slice. And we do this by multiplying the relative frequency times 360. Why did I pick 360 degrees here?
Because the pie is like a circle.
The circle, and how many degrees are in the circle?
360.
360.
You said times 360.
Yes, so to get the size of each slice of the pie, you do relative frequency times 360.
Okay, I see.
And then we use if we want to be extra precise, we use a protractor to mark off each slice. Now, at least on like tests and stuff, I'm not going to give y'all one like the example we're about to see, because that is being super precise. So when we look at a pie chart, the way we would describe the pie chart is to comment on which category had the largest, which had the smallest, stuff like that. So, let's look at a resume example. How many of y'all have had to type resumes sometime while you've been in high school? A few of y'all? Okay. So, if you've had to type one, you probably know the importance of spell checking and proofreading. So typos on a resume do not make a good first impression when you go to apply for a job, a scholarship even, colleges. If they have to get really picky, they're going to start looking for typos. And when you consider applying for like a corporate job, they get thousands of applications. So if they start seeing typos on your resume, even just one typo, this chart says that 40% of them basically throw out your resume. Their no pile, you might as well just say it's their trash can. They look at your resume, there's a typo, and it just goes in the trash. If there's two typos, it's 76% of the time it's going in the trash. Three typos, 90%. And if you got four or more, it's pretty much guaranteed to go into the trash. So just, I don't want to say a bit of real world advice, but if anyone, this is for this year, next year, whatever, if anyone's typing a resume, whether it's for a job, a scholarship, a club, and you want proofread, you can email it to me and I will get it proofread for you. I'll proofread them. I don't mind doing that for you. If y'all need someone to proofread it, I'll proofread any resume, essay, anything like that. Okay, anyways, back to this example. So what they want us to do is create a pie chart to show the data and how frequently resumes get thrown out for typos. So what's the first thing we need to do when we do a pie chart? When it says how to construct at the top, what's the very first thing you do? Draw a circle. Boom, we drew a circle. So, draw a circle. Now, what we need to do is figure out how big of a slice will one typo take up. So how can I figure out how big this one typo slice would be? Relative frequency times what?
360.
Times 360. So what is 0.4 times 360?
Oh, so we don't have to do anything on the table besides like we could go relative frequency? Like
I'm
that?
sorry.
All right, thank you.
144. So we would use, I'm not going to make her use a protractor here, but we would use a protractor to make sure our slice is 144 degrees. And then you just keep repeating that for each one. So the reason I wouldn't ask y'all to do pie charts by hand is to get them exactly precise. It's really painstaking with a protractor. It took me a good probably 15 minutes to get this one lined up exactly.
With a protractor.
With a protractor, yeah.
Thought it'd be easier with one of those.
Well, it would be if I had a giant circle, but my circle's small, so I'm sitting here trying to use a protractor and a ruler and then draw the line.
I got you.
It was, okay, let me draw the chart. So if you had to draw one, I'd maybe only give y'all like 3 categories, and one of them would be like 3/4 of the circle, so it'd be an easy one to draw.
Any AP tests for later at the job, pie chart, like in a conditional section.
I would have to look into that. I don't want to say yes, I don't want to say no until I look into it more. Yes.
So once we get done with like the whole lesson, or we just gonna be working on AP, like go forward, or that's it.
Right, see, like once we get through with all the content,
Yeah.
it'll take us the whole semester. We have 13 chapters to get through. Yeah. What I will say though, since y'all are taking it in the fall, what I'll do is at the end of the semester, give y'all an AP study manual that you can check out. And then through the spring, if you get time and you want to work through it, you can do that. And if y'all, and we'll talk about this in December and January, but if y'all are interested, maybe once a month, if y'all want to like, get together after school or on a weekend, I'll like provide pizza or something, and we can have a study session just to keep everything fresh. Yeah. We'll cross that bridge when we get to it. So on a pie chart, really, if you want to create one, the easiest way to do it in like Excel or something. This one, we created it in a software called Minitab, which is a statistical analysis software. So that's why it started out like that, but then it turned because software created it. So, does anyone need more time to draw the pie chart? Okay, let's go on to section 3.2. So that was all of 3.1. So, I guess I forgot this question first. So what does this pie chart tell us about the number of typos occurring in resumes before the applicant's not considered? What's the main 2 numbers of typos they'll take before throwing it out? 1 and 2 typos. After 1 and 2 typos, most of them get thrown out. Okay, section 3.2. Now we're going to get to numerical data. So we have this little, it's an activity, but it's not an activity. You'll laugh at the name though. It's called cussing your graph. So we're going to learn how to cuss our graphs. And then we'll get to stem and leaf displays. So on the bottom of page 3, you see this figure here. What do you notice about these 3 different distributions of test grades? What do you notice about them?
They look pretty similar.
They look pretty similar, for the most part. Where's the bulk of the grades down here? Yeah, 65, 66, 67, somewhere in there. What about up here? Yeah, somewhere in there. Then what about this top one? 85, 90, somewhere in there. So the central part for each of these is in different positions, isn't it? So that leads us to how do we describe a numerical univariate graph? Remember, univariate means how many variables? One. So first, one thing we can do is look at the center. As we'll see tomorrow, that's the C in CUSS. Center. So discuss where the middle of the data falls. And then there's three measures of central tendency. Once we get through today, maybe through tomorrow, you'll start hearing me say, what's the central tendency and spread of the data? So central tendency is the mean, median, and mode. Now, it may have been a while before y'all used these three words. What's mean? Mean.
Average.
Average. What about median? It's the middle number, but how do the numbers have to be organized before you can get the middle? Least to greatest. Good. What's mode mean? The one that occurs most frequently. That's right. Back in I guess it was 4th or 5th grade, when I learned it, mode is most often. Mode. So the mean or median is typically reported rather than the mode. Dual credit, if you look in Blackboard and you look at your course grade, under it you'll see the median and the average grade. So once we kind of get through this chapter, you'll kind of realize why I show those to y'all. Because if you're above average, that's great. If you're above the median, that means you're on the top half of the class. That's even better. Okay. So what strikes you about these three?
They're different.
They're different. How are they different?
They're
More spread out.
They're more spread out. So this first one is spread way out. That one's a little closer together. And then the third one is really close together. So the next one, the first S, is spread. So that discusses, just like it sounds, how spread out the data is. And this refers to the variability in the data. So there's three main measures of spread. The first one is the range. And remember, range is your maximum minus your minimum. Let me back that out because I kind of went. That's one you'll need to write down. So range is maximum minus minimum. Standard deviation and IQR, which stands for interquartile range. We'll get to those in chapter 4. Range we'll talk about now. These last two we'll talk about in chapter 4. That's really when we're going to start throwing around formulas. And you're going to want your formula sheet. We said remember range is max minus min. And we'll get to the last two in chapter 4. Okay. Next group. What strikes you about these 3 graphs? H and I are more concentrated on one side, and then G is kind of just in the middle. So I starts off low, and then you get to the hill. H, you have the hill first, and then you start kind of going down slowly. And G, it's a little bit more symmetric. So this refers to the shape. That's the overall shape of the distribution. Is it symmetric? Is it uniform? Is it skewed? Bimodal? Etc. So the next few slides, basically the rest of this class, we're going to talk about shape. We're not going to do that activity at the bottom just because of us having to squeeze everything into 3 days instead of 4. So we're going to have to skip that activity. But let's talk about shape. So first, symmetric. What's it mean for something to be symmetric? It's identical on both sides. That's right. It refers to data in which both sides are more or less the same. They may not exactly be the same, but they're pretty darn close to it. If you can fold it down the middle, and it will pretty much line up, it's symmetric. Usually these are bell-shaped. They're a special type. They have a center mound with 2 sloping tails. So let's look at the 3 types of unimodal curves. Did it draw it? I can barely see it up on the screen. But there's a light blue line. Hopefully on your notes you can see it better. Then it kind of starts, goes up, and then back down. That's what they call normal or bell-shaped. Why do they call it bell-shaped? Because it looks like a bell. And I'm hoping it's not like this, but in college, some professors give grades based on what they call the bell curve. Meaning, few will fail, some will get D's, most will get C's, a few get B's, and only the top students get A's. I personally didn't have any professors like that. They gave you the deal in the syllabus, and that's pretty much what they went by. If you met what it said in the syllabus, that's the grade you got. They might curve you up a little bit, but they never went down. Okay, then you have a heavy-tailed, or you'll probably hear me call them fat-tailed distributions. These longer tails mean a larger standard deviation.
Is this one we need to write down every tail?
Yeah. You probably should write down these definitions. underneath each one. And then you have the light-tailed, and that's where they're grouped really close together. Now, on y'all's handout, can y'all see the line? Are the lines drawn or no?
There are
Kind of drawn?
Okay.
Okay. I can barely see them from on the slides. But heavy-tailed, think of it like you just stretch the bell out. And then light-tailed, it's just, you go up real quick and you come back down real quick. Light-tailed distributions have a small standard deviation. They have short tails and small standard deviations. There's not much wiggle room there. Anyone still need some time to write? Okay. Okay, so all of these are symmetric. Whether you're normal shaped, heavy-tailed, or light-tailed, they're all symmetric. You can draw a line down the middle and fold that graph almost exactly in half. Now let's look at something called uniform in shape. So it refers to when data in every class has equal or approximately equal frequencies. So the way to remember uniform is think of like soldiers or even the band in block formation. They all pretty much look the same. Now, it may be kind of jagged because everyone's not the same height, but they're all dressed the same. They're all standing pretty much even with each other. So that's how you remember soldiers wear uniforms, and when they're lined up, they're all pretty much even. So let's look at skewness. So skewness refers to the data in which one side or tail is longer than the other side. And the direction of the skewness is on the side with the longer tail. That's important. The direction of the skewness is on the side with the longer tail. When I was learning stats, this tripped me up every single time. Honestly, it wasn't until I started preparing this lesson for y'all that I'm like, well, why didn't my professors put it like that? I kept wanting to look for the side where the hump was on. But it's not about the hump, it's about the tail. So there's two directions. You can be positively or right skewed, or negatively, which means left skewed. I'll use those interchangeably. So I don't know if you want to write that positively and right mean the same thing, and negatively and left mean the same thing. So what's something that we could think of that hopefully show the negatively skewed distribution? Remember, negatively means that there's a big tail on the left side, everything is clustered over to the right. Hopefully our grades will be that way. That means everybody would make high grades. And not many people would make the low grades. So let's kind of press pause on skewness for a second and think of this example. Suppose they collect data on the time it takes to drive from San Luis Obispo, California to Monterey, California. Some people take the inland route. That takes about 2.5 hours. Others take the coastal route, which is between 3.5 to 4 hours. What shape would this distribution have? Let me ask you this, how many modes do you think this distribution has? Well, they give them to us. There's one. There's the other. How many modes does this problem have? 2. If unimodal means one mode, what would 2 modes mean?
Bimodal.
Bimodal. So what shape is this? This would be a bimodal distribution. It refers to the number of peaks in the shape of the distribution. So we say unimodal meant 1 peak, bimodal meant 2 peaks, multimodal means it has more than 2 peaks. So I gave y'all this answer. What would it be called if it only had 1 peak? Unimodal. Yep, I gave y'all that answer. So that's that last bullet point. Unimodal. So we're going to end today by looking at just illustrations of the different shapes. That way, if you're one that you like to make flashcards so you can get things memorized, this will give you a way to make flashcards. But anyways, let's go back. So unimodal just has 1 peak. Bimodal has 2 peaks. Multimodal has multiple peaks. Then we have our skewed. So skewed negatively, or skewed left, means we have a tail on the left side. Symmetric is exactly like it sounds. It's symmetric. There's no tail. It's just even, exactly in the middle. And then skewed positively means it's got a big right tail. And we also could say skewed right. I think that's it. Let me double check. Yep, that's it. That's it for today. I wanted to get through the first 5 pages. We got through the first 5 pages. Dual credit, that assignment that y'all got today had stuff about, it's got stuff about pie graphs on it. It's got some about bar charts on it.
So we can do some of it tonight.
You can do some of it tonight, yeah. Dot plots, which we've already seen dot plots. Pie graphs, bar charts. Yeah, you can certainly start on some of this tonight.
Is the Monday
Just do Monday.
and Blackboard?
On Blackboard, yes.
Mr. Sullivan, that 3-try system,
Uh-huh.
Blackboard,